To study chemistry, we first have to draw a strict boundary around what we are actually measuring. We define matter as anything that possesses mass and occupies a physical volume. That definition deliberately excludes energy forms like light, heat, sound, and electricity. If it doesn't have mass and take up space, it is not matter. All matter is composed of tiny particles, and the physical state of that matter, whether it is solid, liquid, or gas, is dictated entirely by how those particles are arranged, how they move, and the strength of the attractive forces between them. This animation shows exactly how that kinetic model works. We start with a rigid, tightly packed lattice of molecules vibrating in place, a solid. As we add heat, those identical molecules gain kinetic energy and begin sliding past one another, forming a liquid. Finally, with enough energy, they break their attractive forces entirely, entering the rapid, random motion of a gas. But notice what happens to the individual molecule itself. Nothing. Even as ice melts into water and boils into steam, the internal chemical bonds of the H2O molecule remain completely intact. The physical state of a substance is highly visible, but it is ultimately superficial. Understanding actual chemical behavior requires looking past those temporary physical arrangements to isolate the immutable chemical identity of the particles themselves. To organize these identities, we divide all physical matter into two primary categories based on the uniformity of their composition: pure substances and mixtures. This decision tree provides our initial framework. On the left, pure substances maintain a strictly fixed composition. On the right, mixtures have a variable composition where substances are simply combined physically. We can further divide that mixtures branch by looking at how uniformly these physical combinations are distributed. If the composition is uniform throughout, it is a homogeneous mixture. The constituent parts are visually indistinguishable. The air we breathe and metal alloys like brass fit precisely into this category. If the composition is not uniform, it is a heterogeneous mixture. You can clearly see the distinct phases of the materials involved, like a combination of sand and water, or oil suspended in vinegar. The defining rule for both types of mixtures is physical independence. Regardless of how well they blend, a mixture's individual components always retain their original chemical properties, and they can always be separated by purely physical means. Moving back to the left side of our tree, we find pure substances. These are subdivided into elements, which consist of only one type of atom, and compounds, where two or more different elements are chemically combined. Here we can see the distinction. An element like gold is structurally simple, a uniform matrix of identical atoms. A compound like water relies on a repeating, highly structured lattice built from different elements. For a substance to qualify as a compound, its elements cannot just mix. They must lock together in a strictly fixed mass ratio. That ratio cannot vary without changing the identity of the substance itself. Achieving that fixed ratio requires a chemical reaction. When gaseous hydrogen and oxygen chemically combine to form water, the process is volatile and physically transformative. This reaction demonstrates the compound paradox. We take highly combustible hydrogen and combine it with oxygen, which actively supports combustion, and the result is a stable liquid that extinguishes fire. Unlike a mixture, chemical combination entirely overwrites the physical properties of the original elements. Once they are locked into that fixed ratio, the original elements can only be retrieved by chemically decomposing the compound. The fact that elements combine in these precise fixed ratios required a mathematical explanation. In 1808, John Dalton provided the world's first scientific atomic theory to solve this problem. This historical chart displays Dalton's framework, assigning unique symbols and specific weights. Hydrogen is 1, carbon 5.4, and oxygen 7. By establishing these weights, Dalton proved his fifth postulate: atoms combine in simple whole number ratios reflecting those fixed masses. To make this math work, Dalton established a set of rigid axioms. Atoms are entirely indivisible, impossible to create or destroy, perfectly identical within an element, and completely distinct from other elements. His model successfully explained the macroscopic laws of chemical combination. But this perfect indivisible sphere would shatter once modern tools allowed us to observe matter at the microscopic scale. Modern subatomic physics forces us to systematically dismantle Dalton's assumptions, starting with his most famous error, the idea that the atom cannot be divided. When the Dalton sphere is broken open, we find that atoms are actually composed of smaller subatomic particles. We have a dense central nucleus made of protons and neutrons, surrounded by distinct orbits of moving electrons. Discovering the neutron immediately invalidated Dalton's second major assumption, that every atom of a given element possesses the exact same mass. Look at the scale. Carbon 12, 13, and 14 all have 6 protons, but varying neutron counts give them different masses, classified as isotopes. Inversely, argon and calcium are different elements, but share an atomic mass of 40, classified as isobars, disproving Dalton's claim. Finally, modern nuclear reactions demonstrate that under extreme conditions, atoms can indeed be synthesized or split apart, violating the postulate that they are indestructible. The indestructible sphere of 1808 is obsolete. Accurate chemical analysis relies on a subatomic model where the number of protons dictates the identity of the element, and the number of neutrons allows for continuous mass variation. With the internal structure of the atom defined, we reach the final conceptual boundary, identifying the absolute smallest particle of a substance that can actually exist independently in physical space. An atom is the smallest particle that retains an element's chemical properties, but with the exception of the noble gases, solitary atoms are chemically unstable. They rarely exist on their own. We can see this instability with a single oxygen atom. It is highly reactive, actively seeking out electrons to complete its outer shell. It achieves stability by bonding with a second oxygen atom, creating a smoothly floating molecule. Being one element, it's homoatomic. Placing a stable water molecule next to it, a compound, makes it heteroatomic. Both represent where substances achieve stable independence. This establishes the strict definition of a molecule. It is the true threshold for independent existence. A molecule is the smallest distinct unit that exhibits the actual bulk properties of the substance you observe in the real world. The rules governing matter form a strict hierarchy. Pure substances, encompassing elements and compounds, are locked into fixed mass ratios. Mixtures, whether homogeneous or heterogeneous, are physical combinations defined by their variable ratios. Historically, John Dalton provided the necessary mathematical framework to calculate those compound ratios, but it took modern physics to reveal the divisible, subatomic nature of matter that dictates how those ratios actually form. Mastering conceptual chemistry requires isolating these definitions in your mind. Keep your mixtures separate from your compounds. Distinguish an unstable atom from an independent molecule. And always weigh classical assumptions against modern subatomic evidence. When running chemical reactions, we measure matter in macroscopic bulk, like a turbulent wave of liquid. But actual chemistry occurs purely between individual microscopic particles. Long before we had the technology to prove that atoms even existed, early chemists had to solve this disconnect. They needed a way to predict exact reaction yields without being able to see or count the reacting units. They did this by observing macroscopic changes in mass and formulating what we now call the laws of chemical combination. These macroscopic rules allowed them to deduce the hidden numerical rules governing the microscopic world. By mastering these classical laws, we can construct the mole concept. This is the central mathematical engine required to translate between bulk mass and exact particle counts, allowing us to solve advanced stoichiometric problems. Memorizing standard formulas without understanding the strict integer constraints governing them is a direct path to critical failures on complex, multi-step exam questions. The entire mathematical framework begins with a baseline axiom established by Antoine Lavoisier in 1789, the law of conservation of mass. Mass is neither created nor destroyed in a chemical reaction. This mandates that all chemical equations must mathematically balance. The total mass of the reactants must perfectly equal the total mass of the products. Once that baseline was set, Joseph Proust and John Dalton proved that matter is quantized, not continuous. They observed this through the laws of definite and multiple proportions. A pure compound always contains the exact same elements combined in strict, simple whole number ratios by mass, completely independent of how the compound was sourced or prepared. In carbon monoxide, 12 grams of carbon combines with 16 grams of oxygen. But in carbon dioxide, the same 12 grams of carbon combines with 32 grams of oxygen. The ratio of these oxygen masses, 16 to 32, simplifies to exactly 1 to 2. Elements do not combine in random fractional weights. Because matter must interact in these discrete packages, this integer logic provides the bedrock mathematical foundation for all future molecular calculations. To utilize this integer logic in modern physical chemistry, we have to quantify it at the absolute microscopic level. We use the atomic mass unit, represented by the letter U. This is the universal relative standard, specifically calibrated to equal exactly 1/12 the mass of a single carbon-12 atom. In physical terms, 1 U is mathematically equal to 1.6605 times 10 to the negative 24th power grams, a mass far too small for any laboratory scale to measure. Avogadro's number, 6.022 times 10 to the 23rd, scales atoms to bulk mass. It dictates that atomic mass perfectly equals molar mass. A carbon-12 atom scales to 12 grams per mole, and an oxygen atom at 16 U scales to 16 grams per mole. This scaling applies to compounds as well. We use molecular mass by summing covalent atomic masses, like water at 18 U, and formula mass exclusively for ionic lattices, like sodium chloride at 58.5 U. Avogadro's number is not an arbitrarily large quantity. It is the precise proportionality constant that relates abstract atomic masses to physical laboratory weights. With these exact scaling rules fully established, we can construct a unified system to navigate complex, multivariable conversions. The mole is the central hub. First, converting moles to particles. Multiplying 2 moles by Avogadro's number yields 1.2 times 10 to the 24th molecules. Second, converting to mass using molar mass, converting grams directly into moles. Finally, 1 mole of ideal gas occupies 22.4 liters at STP. Rapid multidirectional navigation across this specific node map is the essential requirement for parsing and solving advanced physical chemistry exam questions. Now we apply this complete system to the process of reverse engineering the exact molecular formula of an unknown compound using only experimental data. The starting point is usually percentage composition, the raw mass fraction of each element present in a sample. This table shows data from an unknown compound consisting of 40% carbon, 6.67% hydrogen, and 53.33% oxygen. The first operational step is to assume a 100-gram sample. This instantly converts those percentages directly into raw mass in grams. Next, we trigger the stoichiometry engine. We divide each mass by the element's molar mass to extract the raw mole values. 40 over 12 gives 3.33 moles of carbon, hydrogen gives 6.67 moles, and oxygen gives 3.33 moles. Then we apply the logic of Dalton's law of multiple proportions. We divide all mole values by the smallest result, in this case 3.33, forcing the data into the simplest whole number ratio, 1 to 1. This simple integer ratio gives us the empirical formula, CH2O. Note this critical distinction. The empirical formula is just the lowest base ratio. It does not necessarily represent the actual molecular formula of the substance. To find the true molecular formula, you have to multiply the empirical formula by an integer scaling factor, which we call n. We find n by dividing actual molecular mass by empirical mass. If a compound has an empirical formula of CH2, meaning an empirical mass of 14, but experimental data shows a true molecular mass of 42, we divide 42 by 14. The scaling factor is 3. Scaling CH2 by a factor of 3 yields the true molecular formula, C3H6. Mastering this pipeline, combining the strict integer laws of early chemistry with the high-speed translation power of the mole, reconciles abstract experimental data into the deterministic, mathematically precise answers required for absolute success. In chemistry, we operate under a non-negotiable physical constraint. The law of conservation of mass dictates that atoms can neither be created nor destroyed. When raw reactants transform, it looks chaotic, but underneath the heat and light, absolutely nothing is created or destroyed. Every atom is accounted for. To model this, we write a skeletal equation. Hydrogen plus oxygen yields water. It perfectly lists the ingredients and products, but as a predictive model, it fails to balance. Look at the left side. We start with 2 oxygen atoms. On the product side, we only have 1. An atom vanishes. This mathematically violates the physics of our universe. To fix it, we balance the equation so atoms on both sides match perfectly. Without a balanced equation, predicting mass or volume output is impossible because the model contradicts the laws of conservation. We enforce the conservation of mass mathematically by adding stoichiometric coefficients. Before we do that, there is an absolute first rule. You never alter the chemical subscripts. Changing a subscript changes the actual physical substance. Instead, we use an algorithm to change quantities, using iron oxidation as our base. We balance the heavier metal atoms first. With 2 iron atoms on the right, we temporarily balance the left by placing a 2 in front of the reactant iron. Next, we have 2 oxygen atoms on the left, but 3 on the right. We cross-multiply to reach parity, giving us 3 O2 molecules and 2 iron oxide molecules. This forces us to update our initial iron coefficient from 2 to 4. Those final numbers, 4, 3, and 2, are the fundamental scaling ratios for this entire chemical system. A balanced equation is the non-negotiable first step of any chemical calculation. It translates a physical process into a solvable mathematical constraint. Now we need to translate those stoichiometric coefficients into physical quantities we can measure. These coefficients give us exact ratios for moles and molecules. And if we're dealing with gases at standard temperature and pressure, they also give us volume ratios. But here is where students fail. Coefficients never represent direct mass-to-mass ratios. You cannot say 2 grams of hydrogen react with 1 gram of oxygen. We are reacting moles, not grams. Because the molar mass of every element is different, attempting a direct mass-to-mass conversion causes the math to collapse immediately. To calculate anything accurately, we have to route all raw physical data into a universal mathematical currency first, the mole. This brings us to the core execution algorithm for any stoichiometry problem. We'll call it the conversion hub. Moles is the central node with 3 pathways: mass, particles via Avogadro's number, and gas volume via 22.4 liters. 4 grams of hydrogen converts to 2 moles. A 2-to-2 ratio bridge yields 2 moles of water, which multiplies to 36 grams. Balance the equation, convert to moles, apply the ratio, convert to the target unit. Strictly adhering to this algorithmic routing guarantees mathematical accuracy. It avoids the fatal trap of mixing grams directly with moles. Real chemistry is rarely perfectly proportional. Elite exams introduce a new layer of complexity: multi-reactant systems. If your starting inputs don't match the required ratio, one reactant will run out first. This is the limiting reagent, and it dictates the absolute maximum product yield. Once that specific chemical is consumed, the entire reaction stops dead, even if other components are left over. You cannot identify this bottleneck by simply looking at raw molar quantities. You have to run a strict mathematical test. Given 3 moles of nitrogen and 6 of hydrogen, we divide available moles by their stoichiometric coefficients. Nitrogen is 3 divided by 1, yielding 3. Hydrogen is 6 divided by 3, yielding 2. The smaller result proves hydrogen is the true limiting reagent. The remaining component, nitrogen, is our excess reagent. It will simply sit unreacted in the vessel after the system locks. Raw molar quantity is deceiving. You only find the limit of a multi-reactant system by testing available material against its specific stoichiometric requirement. Finding that limiting reagent serves one formal purpose: calculating the theoretical yield. Theoretical yield is an idealized mathematical ceiling. It assumes 100% perfect physical execution with 0 loss. But experiments are never perfect. The amount of product you physically gather in a lab is the actual yield, and it is universally lower. This chart shows exactly how much product was lost to physical inefficiency. To measure this efficiency against our theoretical maximum, we calculate percentage yield, the actual yield divided by the theoretical, multiplied by 100. Stoichiometry establishes the rigid mathematical baseline required to measure real-world physical efficiency. When facing complex, multi-step problems in competitive exams, you need strict execution rigor. First, you verify and balance the skeletal equation before attempting to extract a single piece of data. Second, you route all mass, volume, and particle data exclusively through the central mole hub. Finally, you always execute the division test to confirm the limiting reagent before assuming the total consumption of any reactant. These steps form a non-negotiable checklist that prevents the most common critical failures. Internalizing these constraints replaces the vulnerability of guessing with a rigorous error-proof algorithm for navigating any chemical system.